Welcome to today's presentation on deadlock in operating systems. In this session, we will explore what deadlock is, its impact on system performance, and most importantly, how to avoid, prevent, and detect deadlock situations. So let's dive right in. So we've said before that deadlock happens when two or more processes are not able to proceed because each is waiting for a resource that is held by the other. It can severely impact the system performance, which will lead to resource starvation, and also it will lead to application crashes. So to help grasp the concept of deadlock, let's consider a traffic intersection analogy. Now imagine a four-way intersection with traffic lights. Each lane represents a process and each traffic light represents a resource. The four characteristics of deadlock that we've seen before are mutual. The first one is mutual exclusion. So in this scenario, we can say only one car can occupy a lane at a time. The second one is a hold-on way. If a car occupies a lane, it may need to wait for other cars to clear the intersection before proceeding. The third condition is no preemption. Once a car enters a lane, it cannot be forcibly removed, right? Similar to resources held by processes. And then the fourth characteristic of a deadlock is circular wait. So if each car waits for another car to clear the intersection, then a circular chain is formed, which causes a deadlock problem. Now, deadlocks can severely impact system performance, right? It will lead to resource starvation and the crashing of applications, as we just said. So deadlock situations can occur in various real scenarios with operating systems. For instance, imagine a multi-threaded application where the threads are competing for limited system resource, such as memory or network connections. If each one of the threads holds a resource and then waits for another that is currently held by a different thread, then a deadlock happens. Another example in a file system. So if multiple processes may need exclusive access to files or directories, then if two processes hold the file each and simultaneously request access to the other file, then there we go. We have a circular wait, which can lead to a file system deadlock. Now, let's shift our focus to the practical strategies to avoid, prevent, and detect deadlocks, as well as recovering from deadlocks within operating systems. There's actually three ways to handle deadlocks. The first one is making sure that the system will actually never enter a deadlock state. And that's using two main methods, which we'll discover in this lecture. The first method is deadlock prevention, and the second is deadlock avoidance. We'll talk about them in details in a second. The second method to handle deadlocks is to actually allow the system to enter a deadlock state, but then have some strategies to detect that it happened as well as recover from it. Now, some operating systems choose to actually ignore deadlocks and do nothing about them. And that's due to really various reasons, which includes the complexity of resolving deadlocks, performance considerations, the overhead to actually handle the deadlock, and as well as the assumption that actually deadlocks are rare and they're not so frequent. So Windows, for example, prior to Windows 10, had really a limited ability to detect deadlocks and take actions to handle them. However, the default behavior was actually to just ignore them and rely on well-designed software to not create actually software that caused deadlocks. Now, Windows 10 did introduce some enhanced deadlock detection and recovery mechanisms to address this limitation. Linux systems as well do not have active strategies to handle deadlocks, and they do choose to just ignore them and rely on the developers to write good quality code that does not cause any deadlocks. So this will lead us to just the first two options. The first one is to make sure that deadlock never happens, and the second one is to allow it but have some strategies to detect it and recover from it. So let's discover what are these two methodologies about and how they work. So the first one is deadlock prevention. The way it works is to make sure that at least one of the 4 necessary conditions of deadlock cannot hold. So, for instance, if we talk about the mutual exclusion condition, one way to do deadlock prevention is to make sure that at least one resource must be non-shareable, because the mutual exclusion and race condition happens when the resources are actually shareable. So one way to do deadlock prevention is to have resources that are not shareable. But this solution is actually not practical because some resources are naturally non-shareable. You cannot share them. Example is mutual locks, mutex locks, right? The second condition, which we may think to invalidate, is the hold and wait condition. So we may try to enforce a policy which states that when a resource is actually requesting a new resource, we have to make sure that it's not currently holding any other resources. For example, in this figure right here, process P is really already holding resource R1 and R2, and so the policy says we are not going to allow it to request R3 until it puts down R1 and R2. Therefore, we cannot have both the request and the assignment edges exist at the same time. So this will cause actually troubles. For instance, low resource utilization, right? A thread may be allocated a mutex locks for entire execution, yet it only needs it for a really short duration, right? And then we may have possible starvation. So a thread that needs many popular resources may have to wait for an indefinite amount of time, because at least one of the resources that it requires is always actually held, and it is always allocated to some other thread. So this, as you can see, is not again practical, and it may cause performance degradation. Now the third condition, which is no preemption, how can we invalidate that? So we can say, okay, if a process is currently holding some resources and it's requesting another resource that is not yet available and it cannot be immediately allocated to it, then all the resources that are currently held by that process must be released. And those preempted resources will be added to the list of resources for which that thread is waiting, right? So that thread will end up waiting for the new resources that it needs, as well as the resources that it was holding but it had to put down because of this rule. And then that thread will be restarted only when it can regain both the old and the new requested resources at the same time. As you may have figured, this again will cause low resource utilization, and we may have starvation. Now, the fourth and last condition of a deadlock, which is the circular wait. How can we invalidate that to prevent deadlocks? Okay, we can say that we will impose some sort of a total ordering of all the resource types, and then enforce or require that the threads request those resources in an increasing order, right? So for instance, if a thread can initially request an instance of resource Ri, after that, the thread can request an instance of resource Rj only if and only if the order of Rj comes after Ri. Now, what is that order and how can we implement it? That's again open to discussion, but the problem is it's too much overhead to create that ordering and to also enforce it into execution. And in addition, now developing an ordering system or a hierarchy does not in itself prevent the deadlock, but it is again up to the developer to write programs that will respect and follow that ordering.